Hey, welcome back. This is 8.4 on trigonometric substitutions. And this kind of method is not a method you would want to do in general, okay? This is like a worst case scenario, end of the world, I will do this only if they put a gun to my head type situation, right? Okay, so that being said, let's go ahead and take a look at it. What are you doing exactly here? You're trying to kind of get rid of a square root. Right? Substitution. And you do this substitution of an entirely new kind of function. The way it works is it's almost like the reverse of your normal substitution. So for the normal substitution, you might let u equal some function. Okay, so now it's kind of the other way around. You're letting you're making it worse almost. But the way it works is that it gets rid of square roots because you can use the Pythagorean identities. Okay, so if you have a situation, maybe let's just erase that altogether, and that never happened. Right. So if you have a situation where you have an integral and it has a square root that kind of looks like this, what you're going to do, say, is let u equal sine of, well, you want to put an a in there as well. So u equals a sine of theta. Okay. And then you could get your differential du by taking the derivative of this with respect to theta. That would be a cosine theta d theta. Okay. And what would happen? Well, this integral will turn into the square root of a squared minus a sine theta squared times this extra bit of information, a cosine theta d theta. Then you could factor out the a, and you get a squared times 1 minus sine squared, and then you kind of, if you're thinking ahead, you can kind of know where I'm headed there. A cosine theta d theta. You take the square root of a and then multiply it with this other a and factor it out. You'll get a squared integral of the square root of 1 minus sine squared, but 1 minus sine squared is just cosine squared from our Pythagorean identities, right? And then the end result is that square root goes away. And you'll have cosine times cosine, or cosine squared theta d theta. Okay, and then if you get rid of the square root, you can integrate it. If the square root's there, it gets in the way, right? So this is the kind of method that you use to get rid of square roots floating around in your integrals. And there's three different subs. I mean, there's more than three, but don't get creative on me. So you'll have this other one, a squared plus u squared du, and in that case you'll use u equals a tan theta. Okay, because that form will work with 1 plus tan squared equals secant squared. Okay, so this is the first type, the second type, and then the third type, you have the u squared minus a squared version du, and of course you'll use secant because secant squared minus 1 is equal to tan squared, and you can then replace the get rid of the integral by taking the square of tan squared. Okay, so this would be u equals a secant theta. And that's really the only three types of subs. Okay. So let's get in here and kind of get our feet wet. In order to complete the integral, you need to do this weird triangle to help you think through kind of the relationships between the forms, I guess. Let's dive in here and let's just cut to the chase, right? So anyways, section 2, here's how it goes, evaluating. Okay, so here's an example. I have dx all over the square root of 16 minus x squared. We kind of already know the answer to this because it's a sine inverse form, so the answer will be sine inverse of x over 4, right? So we know the solution. Let's see if we can kind of work through this process doing a u sub instead, right? So in this case, or a trig sub. So in this case, since I'm going to let x equal something worse, you know, it seems like it's not going to work. I'll let x equal 4 sine theta, right? And to make everything, I need the differential. To get everything in terms of theta, I need to replace dx. So I'll have 4 cosine theta d theta. And eventually, you're going to want to solve this expression for theta. Okay, and it's for the end step. You'll often have to do back substitution. You want to get everything in terms of x. And that usually involves taking an inverse of a trigonometric function. So you'll have formulas like a sine of cosine inverse. Okay, in order to evaluate that, you may have forgotten how to do that, but usually we use a triangle to do that. I'll show you in the next problem. But here, all we really need to do is solve for theta. Okay, so we have you know, sine of theta equals x over 4, and then take sine inverse on both sides, and you get theta equals sine inverse of x over 4. Okay, for now that's kind of all we need because this problem is so simple. I won't have to go any further than that, but let's go ahead and go at it, right? So here we have the integral. Dx is now 4 cosine theta d theta, and then down below we have the square root of 16 minus x squared. So x is 4 sine theta, x squared is then 16 sine squared theta. Okay, so this thing right here, I could rewrite by like factoring out the 16. So I'd get 16 times 1 minus sine squared theta. And then you could rewrite 1 minus sine squared theta as cosine squared theta. And then you could take the square root of that. That's just going to end up giving you, so this thing equals that, this thing equals that. And that will just end up giving you, what, 4 cosine theta. Okay. Okay, so that's just kind of in parentheses here. So my integral then becomes 4 cosine theta d theta all over, in the end, 4 cosine theta. And then this cancels with this, and you have the integral of d theta, and that's just equal to theta plus c. And then to get it back in terms of x, we can go over here, and yeah, okay, theta is just sine inverse. Hey, that's the answer that I predicted, right? Sine inverse of x over 4. Great. Let's look at one that's a little harder, and this is actually the video quiz question for this section. Video quiz, video quiz, video quiz. Do an alert. Video quiz. All right. So, anyways, here is the guy. Obviously, we don't know how to evaluate this one. Well, maybe. I mean, you know, what it kind of looks like a area underneath a circle, except we need an antiderivative. We don't want just a numerical value. You know, we could apply pi r squared and multiply it by half or something if we knew the bounds on the integral. We're looking for an actual antiderivative, though. Okay, so we're going to have to kind of use this method that we've developed, and it'll work. So the first thing I'm going to do is just simplify it a little bit. I see there's a factor of 4 in there that I can factor out. So this is 4 times 4 minus x squared. That should help simplify things a bit. Then, you know, the square root of a product is equal to the product of the square roots. So that's equal, this chunk is equal to that, and then that's equal to 2 square root 4 minus x squared, right? So I can factor out a 2, and I get the integral of the square root of 4 minus x squared dx. Okay. That form is the sine inverse form, so I need to let I need to let x equal, right? So I need to let x equal 2 sine of theta. Okay, so 2 because this first term here is 2 squared. All right, so I'm going to need all this other information. So the differential is 2 cosine theta d theta. I need to solve for theta eventually for the last step to get everything back in terms of x. So I have then, let's just cut to the chase, right? Theta is equal to, so I divide both sides by 2. I have x over 2, take sine inverse of both sides. I have sine inverse of x over 2. Okay. I'm going to end up having to kind of do this other step over here. So I'm going to leave myself a little bit of room. Okay? And there's going to be one extra thing I need to do to get everything back in terms of x in a real nice, pretty easy to read form. So anyways, what do we have now? I have 2 integral of the square root of 4 minus 4 sine squared theta times dx, which is now 2 cosine theta d theta. I can factor out a 2. I have then 4 integral. And this thing, you know, again, it's going to be one of these. Okay, this is then the square root of 4 times 1 minus sine squared theta. Then I could replace that with 4 times cosine squared theta, and then that'll be 2 cosine theta, right? So actually I have then another 2 I could factor out. It becomes a little hard. You have to be a little careful accounting wise. Then there'll be a cosine times a cosine inside here. So that'll be cosine squared theta d theta. Then this is a trigonometric integral. So these always turn into the integrals from the previous section that we worked in. Okay, so this will end up being 8 times the integral of 1 plus cosine of 2 theta using half angle formula. D theta, we can factor out the 1/2. You get 4 integral of 1 plus cosine of 2 theta, d theta. And then we can integrate 4 times theta plus sine of 2 theta over 2 plus c. Right, so I have 4 theta plus 4 times sine of 2 theta over 2 is the same as 2 sine of 2 theta plus c. Okay. The 4 theta, we can do an easy substitution on that. So it's just going to be 4 sine inverse of x over 2. This thing is a big troublemaker, though. Okay, so how am I going to deal with that? Well, first I'm going to have to use the double angle formula, believe it or not. So this will turn into 2 times sine of 2 theta is equal to 2 sine theta cosine theta, right? So 2 times 2 sine theta cosine theta plus c. Okay. Then what do you have there? Well, I have 4 sine inverse of x over 2 plus 4 sine of theta, which is sine inverse of x over 2, times cosine of sine inverse of x over 2 plus c. Okay. So I had to, you know, the reasoning why I had to convert sine 2 theta into 2 sine theta cosine theta was because I need to eventually be able to simplify this thing and this thing. Okay. The first thing, sine of sine inverse of x over 2 is just going to be x over 2. Okay, that's no big deal. The second guy, I don't know, right? But if you remember from maybe pre-calculus or trig or calc 1, we developed methods for simplifying those kind of expressions. So anyways, I'll have 4 times x over 2 times this cosine, this weird thing here. We can't leave our answer like that. The calculator, the computer isn't going to like it. You can simplify that into a nice looking algebraic expression. Okay, so something in terms of square roots or fractions, something like that. Okay. Okay, so how do I do that? And that's where I left that little region in my chart over here. We're going to use a right triangle. Okay. So here's my angle theta. It's a right triangle. The input of sine inverse then is, this is where your basic identity starts paying. It's opposite over hypotenuse, right? So on this triangle, the opposite is 8x, and the hypotenuse is 2. And then the adjacent side, using Pythagorean theorem, how did that work? X squared plus b squared equals 4. So b squared equals 4 minus x squared. So b equals the square root of 4 minus x squared. So it'd be square root of 4 minus x squared. Okay, so what? Well, for either identity, first off, the sine of sine inverse of x over 2, you could use this triangle to figure that out. The thing inside of it is the angle in that right triangle. This thing right here is going to be your theta in this right triangle. Okay. So the sine of that angle is just opposite over hypotenuse, and if you look at the opposite, well, that's x, and the hypotenuse is 2. So sine of sine inverse of x over 2 is, as promised, x over 2, right here. Then we're also we can also figure out this other guy, right? In this case, we're doing cosine of this angle. You see that sine inverse of x over 2, that angle there. Cosine is what? Cosine is adjacent over hypotenuse. So it's going to be square root of 4 minus x squared all over 2. So our answer is now looking a little more palatable if you have a healthy fear of these inverse trigonometric functions. You don't want to have to deal with them. Anyways, what did we say cosine of sine and inverse was? It's adjacent, so that had been square root of 4 minus x squared. All over hypotenuse, which we're saying is 2. Okay, and that's as good as we're going to get it done. Okay, so our final answer for sine inverse of x over 2 plus x square root of 4 minus x squared plus c. Okay, these problems can be challenging. It could be a lot of work and a lot of little trig identities that you may not remember. But I gave you pretty much every trig identity that you'll need in the beginning of the last video. So hopefully it won't be too overwhelming. Let's look at the next one. So we've been doing sine subs. Let's look at a different kind of sub then. So example. The integral of the square root of 25x squared plus 4 all over x to the 4th dx. Okay, so this time we want do a substitution in here. Okay, so if we rewrote that, what would we have? We would have 5x squared plus 4 all over x to the 4th dx. But the form is a tangent, right? If it has that plus in there, it's automatically a tangent. If it's minus, it's either going to be sine or secant. If plus, it's a tangent. So what do we want? We want our tangent to replace 5x. So we want 5x to equal, and we need it to work in tandem with the a value, right? So it's going to be a tan of x, right? And the a value is 2 because of that 4 that's sitting in there, right? So it's going to be 2 tan of x, okay? Okay, then get your differential, and you can take the derivative of 5x is 5 dx. The derivative of 2 tan x is 2 secant squared x dx. And then we want to isolate dx, so divide both sides by 5, and dx is 2/5 secant squared x dx. Okay, I'm going to go ahead and, use theta all through there. Sorry. So theta, secant squared theta d theta, and then theta d theta. Okay, now I'm going to solve for theta. So theta will end up equaling tan inverse of 5x over 2. And finally, I might as well get my triangle ready in case I need it. So I just like to get all the busy work out of the way. Tangent is opposite over adjacent, and then Pythagorean theorem will give me the 25x squared plus 4. Right there. Okay. Okay, let's box all that junk off. And start our subs. So we have the integral of 5x, the square root of, and what is 5x? 5x is 2 tan theta squared plus 4 all over x to the 4th, and then dx will be 2/5 secant squared theta d theta. This thing in the top, let's clean that up a little, right? So this will equal the square root of 4 tan squared theta plus 4. That will equal, factor out the 4, tan squared theta plus 1. That will equal square root of, you replace tan squared plus 1 with secant squared, and then that'll equal 2 secant theta. Okay, so that numerator will just be 2 secant theta. Okay, so I'm going to replace it. Wrong color. Replace it with 2 secant theta up top, all over x to the 4th times 2/5 secant squared theta d theta. Oh, whoops, I could replace x to the 4th as well. So what is x? X, so I have 2/5 tan theta to the 4th power. Well, that's like a mess, right? I could factor out 4 from the, so you'd have 2 all over 2 over 5 to the 4th power times 1 factor of 2/5 times the integral of secant cubed theta all over tan theta to the 4th power d theta. And then I could clean up this constant a bit. So 1 factor of 2/5 will cancel out and get 2 all over 2/5 cubed. Integral of and I'm going to rewrite this, probably mess around with it in terms of sines and cosines, right? So secant cubed would be the same as 1 all over cosine cubed theta. 1 over tan to the 4th is cotan to the 4th. Cotan to the 4th is cosine to the 4th all over sine to the 4th theta. And then let's clean up that stuff. So I have 2 times the reciprocal of 2/5 cubed, which will be 5/3 cubed, which is 125 all over 8. And then I can reduce this a little, so I'll have kind of a weird mix of cosine theta all over sine to the 4th theta, d theta. Okay. And then I can simplify the factor out front and the 125 over 4. On the inside, I have cosine theta times, looks like a cosecant to the 4th. That's not very helpful. How about maybe going cosine over sine times 1 all over sine cubed, maybe? Maybe that works. Can you do a sub for... Okay, what do we have then? 125 all over 4. That would be like cotan times cosecant cubed. I don't want to go on that route, but I think I may have to. So it's going to work like a secant tan, right? So I have cotan times cosecant cubed theta d theta, and that will equal 125 over 4. I'm going to push back on a cotan and a cosecant, so I'll end up with cosecant squared theta times cosecant times a cotan theta d theta, and then you could do a u sub on your cosecant, and your du will be negative cosecant theta cotan theta d theta, and then your d theta will be negative du all over cosecant theta cotan theta. And so you'll have 125 over 4 times the integral of u squared times your cosecant theta cotan theta times d theta, which is now negative du all over cosecant theta cotan theta. So that junk cancels. You can factor out a negative 125 over 4 integral of u squared du. So that would be negative 125 all over 12 u cubed plus c. Back subbing, I have negative 125 all over 12 times cosecant of theta cubed plus c. And then you could use your triangle, right? Because it's really cosecant of tan inverse of 5x over 2. But tan inverse of 5x over 2 is just theta. So you can use that triangle to replace the cosecant. Okay. So cosecant is just 1 over sine. So it's hypotenuse over opposite. So we'll have the square root of, so this will equal negative 125 over 12 times the square root of 25x squared plus 4 all over, so what did we say, hypotenuse over an opposite, because it's cosecant. So hypotenuse was the 25, square root 25x squared plus 4. Opposite is 5x, so I'll put a 5x downstairs. And this is cubed. C. If I cube that 5, I get 125. So the 125s will cancel. And I'm sort of being left with then a negative 25x squared plus 4 to the 1/2 to the 3rd power, which will be 3/2 power. And then down below you'll have a 12 and an x cubed, and then plus c. Moving on. So let's do one where we actually evaluate, and on top of that, this will be a secant version. So we're going from 4 to the 6, and our integrand x squared all over the square root of x squared minus 9 dx. Okay, so this time it looks like it's a secant with a value of 3, so we're going to let x equal 3 secant theta. Dx will be 3 secant theta tan theta d theta. And then theta will equal secant inverse of x over 3. And then let's just go ahead and get our triangle out of the way for our back subs. Secant is 1 over cosine, so this will be hypotenuse over adjacent. And then the third side, by Pythagorean theorem, will be x squared minus 9. Okay. Okay. So let's go at it, and substituting in, I have 9 secant squared theta all over the square root of x squared minus 9. All right, so x squared minus, what is that? Square root of x be 9 secant squared theta minus 9. And then dx is now 3 secant theta tan theta d theta. And then we can do some simplification on this thing. That's going to be 9 times secant squared theta minus 1, which equals 9 tan squared theta, which of course is 3 tan theta. So the 3 in the bottom will cancel with that 3. There'll be a 9 to factor out when all is said and done. Integral of, in the top, secant cubed theta, tan theta, all over tan theta, d theta. Okay. And then we can simplify, and we end up with one of these nastier integrals. I did this integral at the end of the integration by parts video. At the end of the day, this turns into 9 times secant theta tan theta over 2 plus the natural log of the absolute value of secant theta plus tan theta over 2. And then plus your integration constant. Now we can use the triangle to replace all of that stuff. So what am I getting? I have 9/2 times secant theta. Secant is just 1 over cosine, so that's going to be adjacent over hypotenuse times tan, which is sine over cosine, which is opposite over adjacent. And then plus 9/2 times the ln of the absolute value of 3 over x plus the square root of x squared minus 9 all over 3 plus c. And that's pretty much it. Do some simplification and make it look a little prettier. Whoops, we're not plus c-ing. Sorry, buddy. You're not done. Yeah, we have to evaluate, right? So it's from 4 to the 6. From 4 to the 6. That's going to make things worse for us to stomach. So 9, the 3's cancel here, so you're ending with 9 square root x squared minus 9 all over 2 plus 9/2 ln absolute value 3 over x plus x squared minus 9 all over 3 from 4 to the 6. And then plug in 6, so get 9, square root of 36 minus 9. 36 minus 9 is 27, which is is 3 root 3, right? So it'd be 9 times, 3 root 3, and then it seems like it should be all over 2. What did I miss? There's a 6. There's an x I missed. That's what I was wondering why it's not working out. So it'd be, what are we putting in? 6? So it'd be 3 root 3 all over 2 times 6. So it would be like 27 root 3 all over 2 times 3 times 2. So 3 into there, it'd be like 9/4. Sorry. What did I screw up then? It's the x over 3, ain't it? I put 3 over x. I wrote cosine instead of sine. I apologize. It's this guy right here. Zoop, zoop. Just get rid of that. So it'd be x over 3, hypotenuse over adjacent. X over 3. So we have 3x over, whoops, these 3 times 3 is 9, with a 9 up there. It's just going to be over 2. Yeah. Okay, so that's better. Sorry. So this will be plugging in 6. You get 6 over 2, which is going to be 3 times 3, which is 9. And then square root of that will be 36 minus 9, which will be 27, which is 3 root 3. So you end up with 9 root 3 plus 9/2 ln of the absolute value of 2 plus 3 root 3 over 3, so that would be root 3, minus, plug a 4 in there, you get 18, plugging in a 4, whoops, not 18, 16 minus 9 is 7, so when you plug in a 4, you'll get 6 root 7, it seems. Trying to do it in my head, it's not working out very well. I apologize. So it's 12 over 2 root 7. What did I forget? Oh, it's a stupid 3 there. That shouldn't be there. So this will be then 4 over 2 is just 2, and then root 7. And then minus 9 halves ln of absolute value of 4/3 plus root 7 over 3. Jeez. And then you put that in your calculator, which I already did. It's 12.64. Yay. Okay. So yeah, kind of a nightmare with respect to recording. This is why it's so important to have nice looking work, not sloppy work with numbers all over the place, because the problems are just going to get longer, as you go through your program. Anyways, let's look at one last one where we have to complete the square. This is number 37, I guess. Let's find one in the book. I'm not happy with number 37. It's like a bummer. What is this? 9 point something. This is 8 point something. So there we go. So we have simple integral x squared all over the square root of 2x minus x squared dx. Okay. So in the denominator, I got to complete the square. So I have x squared all over the square root of. I'm going to factor out. Okay, so I'm going to factor out the negative, and then I'll have x squared minus 2x, and I have to add something in, and then immediately subtract it. But because it'll be negative, you're immediately adding it, dx. So it's always b over a squared, so negative 2 over, so b over 2 squared, sorry, b over a is from the vertex. So negative 2 over 2 is negative 1 squared is 1. So then you immediately add 1. Rewriting and doing some factoring, we would end up with 1 minus x minus 1 squared dx. So we have what looks like a u sub for x minus 1. For the beginning of this, that's probably what I would do. du is dx. And so x will be u minus 1. Or maybe we should just make the sine inverse that equal to that. Man, this is a... Jeez, people. So this would be u minus 1 all over the square root of 1 minus u squared du. And then you could rewrite it as u all over the square root of 1 minus u squared du minus the integral of du all over 1 minus the square root of 1 minus u squared. That's just sine inverse of u. So that first one is kind of a troublemaker, so we need to let our u equal sine of theta, and then du will be cosine theta d theta. And then d theta is equal to, I guess we don't need d theta here. I just need to get my triangle stuff. So du is equal to that. Right, so theta is equal to sine inverse of u. And then we have our triangle. So you think of u as u over 1. So opposite over hypotenuse. This will be the square root of 1 minus u squared. For future reference. Okay, so going back to the integrals then, I have sine theta in the numerator. Downstairs I have the square root of 1 minus sine squared theta. And then du will be cosine theta d theta. And then minus this other thing, which is just sine inverse of u, which is x minus 1 plus a constant. At this point then you have the integral of sine theta cosine theta all over this thing, which will end up being the square root of cosine squared theta, which of course will just be cosine theta. So you get cosine theta in the bottom, d theta minus sine inverse of x minus 1 plus c. Cosines say goodbye. You have the integral of sine theta d theta minus sine inverse of x minus 1 plus c. Then integral of sine is negative cosine theta minus sine inverse of x minus 1 plus c. Then you go back to your triangle. Cosine is adjacent over hypotenuse. So that will be square root of 1 minus u squared, right? Because the adjacent is that and the hypotenuse is 1. Minus sine inverse of x minus 1 plus c. And then you finally get 1 minus x minus 1 squared minus sine inverse of x minus 1 plus c. Okay, that'll do it, and I'll see you next time.